It begins in the heat of the equator, not in a kitchen, but in an agro-industrial hub where the aroma of cocoa is masked by the scent of steel, insulation foam, and diesel. Here, tons of melted chocolate are not delicately poured into molds, but pumped into reinforced stainless steel tanks with heating jackets and internal stirrers calibrated to the 10th of a degree. This isn't a gourmet process. It's a logistical operation designed to keep a complex organic emulsion alive across oceans. Because liquid chocolate is not just a food, it's a substance governed by forces more delicate than they seem. Underneath its creamy texture lies a scientific paradox. Chocolate behaves like a non-Newtonian fluid. Its viscosity changes depending on how it flows and how it's stirred. The moment it cools, even slightly, its inner components begin to separate. Cocoa butter starts to crystallize. Sugar particles drift out of suspension, and what was once smooth becomes sticky, dense, and immobile. It's no longer cargo. It becomes a solid mass trapped in its own container. That's why transporting chocolate isn't about keeping it hot. It's about maintaining what engineers call a thermal homogenization window, a narrow temperature corridor between 40 and 45 degrees Celsius, where chocolate stays fluid, balanced, and ready to move. Outside this window, chaos begins. Inside, stability reigns. This is the invisible corridor that defines the success or failure of a shipment. To understand the scale of the challenge, imagine a ship designed for oil, one that uses layered coils and internal convection currents to keep crude moving across continents. Now, replace that oil with liquid chocolate. Suddenly, the engineering becomes more precise, the risks more unforgiving. Oil doesn't crystallize at 39 degrees. Chocolate does. That's why many chocolate tankers are now inspired by maritime heating systems. Double-walled tanks with integrated heat coils and carefully orchestrated agitation, designed not just to transport, but to protect molecular structure in motion. But even heat is not enough. It's the movement, the way chocolate flows, folds, and circulates within itself that defines its survival. Too much agitation, and the structure breaks down. Too little, and particles settle at the bottom, eventually clogging valves and nozzles. Every shipment is a mechanical ballet. Agitators turn slowly, heat pulses gently, and the entire mass of fluid breathes in motion, synchronized like an orchestra of rotating blades and thermal sensors. In this context, temperature is no longer a number. It's a mission. Engineers must maintain the rheological balance of the chocolate, keeping its yield stress and viscosity in a precise range, between 1,000 and 3,000 centipoise. Between 30 and 60 pascals of flow resistance. These values aren't theoretical, they're practical barriers. Cross them, and the chocolate won't just stop flowing. It will destroy the very system designed to carry it. This is the silent science behind your chocolate bar. Not just the plantation, the harvest, or the recipe, but the mechanical intelligence that moves a living fluid through ports, terminals, roads, and borders without letting it turn into a block of industrial waste. It's not visible on the supermarket shelf, but it's there, in every pore, every pump, every kilometer. Transporting chocolate is not about indulgence, it's about precision, a delicate harmony between heat, movement, and time. And it all begins here, in this narrow window between fluid and failure. At first glance, the tanker seems like any other, cylindrical, polished, insulated. But the substance it carries isn't oil, milk, or molasses. It's chocolate in its liquid form, and it's moving under a strict thermodynamic contract. The margin for error is so narrow that a 2 degrees Celsius drop, just 2 degrees, can stop everything, not gradually, instantly. Inside these tanks, chocolate travels under conditions that appear stable from the outside, but stability is an illusion. In standard vegetable oil tankers, heat is passive. Warmed walls, occasional stirring, insulation to slow down cooling. That works for oil. It does not work for chocolate. The reason lies in particle behavior. Cocoa solids, even when finely ground, begin to separate if left too still. They descend slowly, like silt in a river, until they accumulate at the bottom. If the tank isn't in constant, delicate motion, the result is sedimentation. And the first component to go solid is also the one most essential for flow: cocoa butter. This is where engineering steps in. The solution came not from chocolate factories, but from ethanol production. Seed reactors that rely on pulsatile movement. The adaptation was elegant. Low-speed thermal stirrers combined with laminar flow, allowing for continuous internal motion without introducing shear stress. These systems don't whip or churn. They circulate, gently, relentlessly, keeping cocoa particles suspended without damaging their structure. The effect is measurable. In a controlled study at the Swiss Institute of Food Engineering, 2 identical tanks were loaded with the same batch of liquid chocolate. One was left with standard thermal control, no agitation. The other employed laminar flow stirrers. After 18 hours, the non-agitated tank exhibited a 4-fold increase in outlet valve resistance, caused by semi-solid accumulation at the base. The agitated tank, stable, uniform, still flowing. But numbers alone don't convey the stakes. In 2023, a transcontinental shipment of chocolate from São Tomé to Rotterdam was abruptly returned to port. The reason? The product inside, 16,000 liters of what should have been fluid chocolate, had hardened near the nozzles. A post-shipment sensor analysis revealed the truth. During a 2-hour delay at the departure terminal, auxiliary power had failed. Temperature dropped to 39.7 degrees Celsius. That was enough. Recrystallization had begun. By the time it reached European waters, the damage was irreversible. These are not extreme cases. They are common boundaries. In liquid chocolate logistics, heat alone is never enough. It's the precise orchestration between thermal retention, particle agitation, and material insulation that prevents collapse. Each factor works in unison, like instruments in a chamber ensemble. Break the rhythm, let one play out of tune, and the entire performance unravels. Chocolate, for all its softness, demands rigor. A tanker may look robust, but it holds something as sensitive as life, because this isn't just the transport of a product. It's the maintenance of a state, a fragile molecular balance held together by temperature, time, and movement. The cost of failure isn't just financial, it's systemic. When chocolate freezes in the wrong place, the entire chain, from the farmer to the factory, pays the price. A thermometer, in most tanks, is a symbol of reassurance. A simple number, displayed on a digital screen, marking the temperature of the walls, the air, the outer layer of a fluid. But in the world of chocolate logistics, that number can be misleading. Because chocolate doesn't fail from the outside in, it fails from the core outward. And by the time the thermometer shows a problem, the process of solidification may already be underway, hidden in silence. Chocolate cools in layers. Its outer shell is the first to feel the cold, the first to crystallize. But standard sensors, designed for vegetable oils or dairy, often measure only 1 or 2 points. They assume uniformity. They assume the fluid is homogeneous. But in a 20-ton tank of chocolate, uniformity is a myth. Temperature gradients form quickly. The top may read 43 degrees Celsius, while deep within, near the bottom curve of the tank, chocolate begins to thicken. And once thickening begins, viscosity rises exponentially, increasing flow resistance and generating heat spots, which can accelerate phase separation instead of preventing it. That's why modern chocolate transport has begun to move away from pure temperature sensing and toward flow-based intelligence. The breakthrough came from another fluid: milk. In dairy microfiltration plants, inline viscometers are used to track subtle changes in resistance as milk passes through narrow membranes. These viscometers don't just measure temperature, they measure the behavior of the fluid in motion. Chocolate engineers adapted this principle. Now, high-end transport tanks use viscometric feedback loops to regulate heating zones in real time, not based on what the thermometer says, but based on how the chocolate flows. The difference is dramatic. In a logistics trial conducted in southern Germany, two identical tankers were loaded with 18,000 liters of liquid chocolate and kept above 43 degrees Celsius during transport. One used traditional thermal monitoring, the other used a 3-point viscometric system. When analyzed post-delivery, the traditional tank showed 12% loss due to partial solidification near the mid-layer. The viscometer-controlled tank delivered the entire volume without viscosity drift. That precision is not just a technical achievement, it's a functional evolution. A Belgian transport company, operating across France, Germany, and the Netherlands, has implemented multi-layered viscosity sensors in its trailer fleet. These sensors divide the tank into 3 horizontal strata, each feeding independent heating elements. Instead of relying on a central command, the tank responds like a living system, adjusting heat, flow rate, and stirrer speed to maintain internal equilibrium. Since implementation, they've reduced in-transit solidification incidents by more than 85%. This is more than innovation, it's a shift in philosophy. Temperature, once seen as the only metric, is now just part of a wider diagnostic web. Engineers are beginning to treat chocolate not as a passive mass to be heated, but as a responsive medium, one that needs to be sensed, interpreted, and assisted in motion. A thermometer reads the surface. A viscometer listens to the core. It doesn't ask what the chocolate is, it asks how it behaves. In the fragile hours between factory and destination, that distinction makes the difference between delivery and disaster, between a product that pours and a product that clogs. Between food and failure, there's a quiet revolution taking place in the world of agricultural logistics. And it begins not with new roads, bigger ships, or faster trucks, but with a change in how we see the cargo itself. For decades, chocolate in its liquid form has been treated as just another commodity to be moved, a load to be kept warm, shielded from the cold, and delivered on time. But the truth beneath that surface is far more complex. Chocolate is not passive. It's not inert. It behaves like a living system, one that responds constantly to its environment, evolving second by second during transport. To move it correctly, engineers must treat chocolate not as a product, but as a fluid in dynamic balance. It is sensitive not only to temperature, but to flow rates, pressure differentials, microscopic shear forces, and the sequence of thermal events it experiences across time. A single drop in external temperature may seem insignificant, but to the molecular structure inside the tank, it can trigger a chain reaction, from stratification to crystallization, from minor resistance to total blockage. In this sense, chocolate transport becomes less about containment and more about choreography, a continuous alignment of energy, motion, and structure. This understanding has reshaped not only the equipment used, but the entire mindset behind cocoa logistics. In an experimental initiative led by Mars Logistics, one of the most data-driven cocoa handlers in the world, a pilot fleet of tankers between Ghana and France was equipped with adaptive routing intelligence. The system didn't just calculate the shortest or fastest route, it integrated real-time weather conditions, road temperature forecasts, and projected cooling rates inside the tank. When a cold front formed over the Bay of Biscay, the system recalculated the entire trajectory, steering clear of the risk zone and maintaining thermal balance throughout the journey. The outcome was a delivery that arrived fully fluid, with no mechanical intervention required. But more importantly, it marked a turning point. Route planning, once a matter of fuel and timing, had become a function of materials science. Beyond transit, the tools of diagnosis have also evolved. Engineers now analyze flow rate curves during unloading, looking for anomalies that indicate viscosity loss, partial crystallization, or tank stratification. Pressure feedback from nozzle heads is no longer just an operational detail. It's a fingerprint of the cargo's internal life. Each delivery tells a story, not just of distance traveled, but of structural integrity maintained. In this new era, transporting liquid chocolate is not a simple matter of insulation and movement. It's a process of preservation, of maintaining the internal coherence of a sensitive, multi-phase substance under constant environmental stress. The tanker is no longer a container. It is a vessel of equilibrium, a moving chamber that must adapt in real time to preserve the state of a food that refuses to stand still. Heat is no longer a shield. It's a medium of communication. Agitation is not turbulence. It's dialogue between particles, and sensors aren't just monitors. They are translators of behavior. Transporting liquid chocolate is not about keeping it hot. It's about keeping it molecularly mobile, stable, flowing, and alive. What was once treated as a silent cargo now demands interpretation, intelligence, and care. Because behind every shipment lies a question that modern logistics must learn to answer. How do you carry something this delicate, this reactive, across a world that is constantly changing? The answer is not in scale, but in understanding, not in brute force, but in precision. And in that precision lies the future of food logistics, one molecule at a time.